Okay, so in this video we're going to focus on the idea of what it means for a function to be one-to-one. It's an important idea when we start talking about functions. And so I have at the top of the screen the more formal definition of what it means for a function to be one-to-one. So for all values a and b, which are in the domain of a function, if we have two function values that are the same, then the x values, a and b, have to also be the same. So again, this is a little bit more formal definition. In the first couple of examples here, I'm going to work with a little bit more informal definition. So informally, what we learn from the definition of what it means to be one-to-one is that if we have a function that's one-to-one, we cannot have two different x values pointing us to the same y value. We cannot have two different x values pointing us to the same y value. Right? If we get the same y value, then that implies that the x values must be the same. Okay, so let's take a look at this first example. And so I've got a set consists of three elements, a, b, c, and I'm going to define a function from this set to that same set. So real quick, these are important when we talk about a function. We have to define a function from one set to another set. We kind of sweep that under the rug in college algebra. Don't talk about that a lot. But this first set is called the domain. We do talk about that in college algebra. And we define a function from the domain to a second set called the codomain. A little bit different from the range. Right, so those really have to be in place for us to fully understand a function, going from the set ABC to the set ABC, and the exact assignments of the function are given here. So we do this, I think, in our algebra classes. We draw the domain and codomain. And then we just make a little diagram representing how the function's defined. So a goes to b, b goes to c, and c goes to a. Right, and maybe this is just a good visual way that we can see this function is one-to-one. What we set up here was we can't have a situation where two different x values point to the same y value, and if we look at our diagram we can see that that is not happening. Only one x value going to one y value for each of the elements. And so this function is one-to-one. And we kind of are just doing this by looking, but again, we don't have a situation where two different x values point to the same y value. So let's take a look at this second example. And so all I've written down is how the function is defined. I left out this part, that the function is going from x to x again. So we've got the same domain and codomain. Right, but what if we make a diagram of this function, same domain and codomain? See something a little bit different. A goes to b again, and also b goes to b, and c goes to a. Okay, so a couple of things. First thing is, again, something we don't say in college algebra is that the y values that end up getting used from the codomain are called the range. So the range in this case is just the elements a, b, which is not equivalent to this setup here, which is the codomain. And that's going to lead into another issue that we'll talk about in another video, but that again is something we don't talk about in an algebra class, right? But does become important if we want to get into and understand what functions are. But that's a little bit beside the point of, is this function one-to-one? This function is not one-to-one because we can see I've got two different x values pointing to the same y value. Right? So if we want to go and verify that a function is not one-to-one, then all we have to do is find two y values that are the same. Right? So f of a and f of b are the same because these are both equivalent to the y value b, but the x values are not the same. Right? So we got two y values that were the same, but they were the result of two different x values. And so that would verify that the function is not one-to-one. Okay, so these first two examples were maybe a little bit more informal. If we want to get into a little more formal ideas, here's a function. Now this function, nothing complicated, that's just a linear function. You should have seen those in your algebra class, going from the set of all real numbers to the set of all real numbers. And you know that makes sense because if you think about the graph of a line, this has a y-intercept at -2 and a slope of 3, so something like this, just to make a quick rough sketch. Right, you know that the domain and the range of a linear function are both all real numbers, right? So this domain and codomain makes sense. And if we want to verify that this function is one-to-one, you might remember talk about something in algebra called the horizontal line test. If the graph of the function passes the horizontal line test, then it is one-to-one, meaning that if you graph the function and a horizontal line touches only once, which in this case that's going to happen no matter where we pass a horizontal line, touch only once, then this function is one-to-one. But if we want to verify this using the definition up here, here is how we would do that. We would let a and b be any real numbers, right? And so the only reason I'm saying that is because I want to let a and b be any two arbitrary numbers from the domain. And then we're going to start with, from our definition, we're going to start with the hypothesis. Right? This is an if-then statement. If this is true, then this must be true. And we're going to see if we can work our way down to that conclusion, that A must be equal to B. So if we start with that f of A is equal to f of B, okay, so I'm going to go back to my function and plug A in for x, and also go back to my function and plug B in for x. Right, so over here it would be 3a minus 2 equals 3b minus 2. And then I'm just going to do some algebra on both sides, add 2 to both sides. That would leave me with 3a equals 3b. And then of course divide both sides by 3. Right, so starting with this assumption, we end with the conclusion that those two x values must have been the same. And so that verifies that the function is one-to-one. Now, if we were to get stuck in our algebra anywhere in here, that might be a pretty good clue that the function's not one-to-one. Of course, having some knowledge of the graph of the function would help us to know whether or not the function is one-to-one as well. So let's look at another function. X squared minus 3 from all real numbers to this set, which is the range of the function, right? You might remember that this function looks something like this, shifted down by 3. So of course does not pass the horizontal line test. That tells us it's not one-to-one. What if we attempted to verify that this function was one-to-one? Maybe we forgot what the graph looked like and we're just going to jump in. We think, well, this seems like it might be one-to-one. What's going to happen here? This side would be a squared minus 3. This side would be b squared minus 3. So of course I can add 3 to both sides. A squared equals b squared, and the way we could try to get rid of the square is if we take the square root. But remember, when you take the square root of something squared, you end up with an absolute value. A lot of people forget that. Equals absolute value of x. And this fact creates, gives you two equations. You end up with a plus or minus. You might remember doing that from algebra. So you would actually end up with something that looks like this. A equals plus or minus b. Right, or equivalently on both sides you would have an absolute value. Right, but either way, you didn't really end up with the conclusion that a was equal to b. In fact, what I ended up with here is that a could be either positive b or a could be negative b. So it looks like we can't conclude that a and b are the same. Right? So that might be a hint that this function's not one-to-one. And so what we need to do to prove that the function's not one-to-one is we need to figure out a y value that is a result of two different x values. And any number of ways you could go about doing that. I'm going to work right here. And let's see. If I was to set this function equal to 12. Now it looks like I kind of just randomly selected a y value. And I kind of did, but what happens if I solve this for x? I'm sorry, that isn't the y value that I want. I actually want to pick 6, not 12. Right, so that if I solve this for x, add 3 to both sides, and now I take the square root, I get plus or minus 3. Right, so why did I do that? Because that tells me that these two different x values will both give me that y value, 6, right? So this will verify that the function is not one-to-one, because if I plug 3 into my function, I get 3 squared minus 3, which is 6. If I plug negative 3 into my function, I get negative 3 squared minus 3, which is also 6, right? But 3 is not equivalent to negative 3. Right? So two different x values that gave me the exact same y value, and so really just showing this is all you need to show to verify that the function is not one-to-one, although you might have to go through some other work, some trial and error to get to that point, but really this is all that we need to see in the end. So hopefully that gives you an idea of what it means for a function to be one-to-one or maybe not one-to-one.